sliding window flow control. With stop and wait flow control in general is to make sure our sender doesn't send too fast. The sender sends packets or frames to the receiver. The receiver has a limited amount of buffer to receive those frames. If the buffer overflows, then we'll lose packets, which is bad. So what we do is that the sender limits the rate at which it sends such that it doesn't overflow the receiver. With stop and wait, the sender sends one frame, must wait for an ACK to come back, and then it's allowed to send the next frame and so on. Stop and wait for the ACK to come back. With sliding window, the sender is allowed to send multiple frames, up to a window size of frames. So there's some parameter now, which is more efficient when we have a large propagation delay compared to our transmission delay. We saw that there's the introduction of a sequence number, and what we finished with last week, we looked at the operation of the window, but what we finished with last week was some example which you had the colour printout of, in some scenario, if we had a maximum window of 3, we saw what happens, especially from the sender's perspective of the window, where the green boxes indicate the number of frames we're allowed to send, the red boxes indicate the frames that we've sent, but yet we haven't yet received an acknowledgement, and later we have the grey boxes, the frames that have been acknowledged. And we see that in this example, where we had a 100, let's say a 100 millisecond transmission delay and a 200 millisecond propagation delay, note the propagation delay is is larger than the transmission delay in this example. With a maximum window size of 3, we get to transmit 3 frames, and then we must wait for the ACK for the first frame to come back. Because of the large propagation delay, 200 plus 200, so there and back is at least 400 milliseconds, then we transmit 3, that's our maximum window. We cannot transmit any more, we must wait for the ACK to come back. So we're not achieving our best efficiency here because we spend some time waiting. And it turns out it repeats like that as we keep going. We receive the ACK back, allowing us to send one more, another ACK, allowing us to send frame with sequence number 0, and so on. Send 3, now wait for the ACK for the first of those 3. And then we could keep going forever like that, as long as we have data to send. In this case, the window of frames, so I'll just scroll down a bit. The window of frames, for example, frames 0, 1 and 2, the time to transmit them is less than the time to get the first ACK back. The time to transmit the first 3 is 300. The first ACK comes back at time 510. The window is a size such that we'll still have to wait before the first ACK comes back. That is, it leads to inefficiencies because we spend some time waiting. To improve upon this, we'd like to be transmitting frames here. That is, spend no time waiting. And the way we do that is to increase the window size, allow us to send more frames. A window size of 4 would allow us to send 4 frames, take us to 400. Of 5 would allow us to send 5 frames, take us to 510. 6 allow us to send 6 frames before waiting for the ACK. And if we had 6 frames, we'd spend the first 510, in fact the first 600 time units transmitting, and we'd receive the ACK back while we're transmitting, allowing us to send another one. Many seats down the front, there's a whole row at the front here, there's some down the front here. 3 hours of lecture, so make sure you can hear, you're not annoyed by someone else who's talking to you all the time. so sit down the front if you wish. We have 81 students in this course. There's about 80 seats in this room, so the last student can sit right at the front in my chair. Actually, I think someone's withdrawn, so we may be safe. So we care about the efficiency of our protocol, and in this case we see now it depends upon our window size. The larger the window, the more frames we can send. And depending upon the propagation delay, if we have a window large enough, we'd be able to always transmit frames. And that's what we saw in the last example, which is on the next page, where we had a window of, in this example, of 7. We're allowed to send 7 frames. We keep transmitting frames, we keep transmitting. While we're transmitting that window of frames, we receive the first ACK back, allowing us to send 1 more. We transmit that 1 more, we receive another ACK back. And we see the green boxes in our window. We've always allowed to send at least 1 frame. Here we're allowed to send 1 more, here 2 more, transmit 1 more, 2 more. If we keep going, we're always allowed to send another frame. There's no time spent waiting. This is the best we can do. Okay, we cannot send any more than all the time. So this is the optimal case in terms of efficiency. And we calculated some numbers. Under the same scenario, depending upon the window size, the first case in the first slide, we had a window of 3, we got about 53% efficiency. When we have a window of 7, on the next page, we got 90%. And in fact, another one which we mentioned was if we have a window of 1, which is stop and wait. Stop and wait is a specific instance of sliding window, except the window is 1. With stop and wait, 1 frame, wait for the ACK. 1 frame, wait for the ACK. With a window of 1, the efficiency is about 17%, 17 or 18%. In the same scenario, increasing the window size increases our efficiency of the protocol. 90%, why? Because this is the second one here, we're always transmitting. The efficiency in this case is the rate at which we deliver the real data. In the example, we're always transmitting, so we're transmitting 100% of the time, but in the question, 90% of that was data, real data, the other 10% was header. So we say, in terms of delivering real data, although we're transmitting 100% of the time and receiving frames 100% of the time, we're not only receiving real data 90% of the time. The other 10% of the time we're receiving header. So that's why we reach just 90%. We cannot go any higher than that. If you set the window to 8, you'll also get 90%. You set the window to 1000, you'll also get 90%. You see, in terms of efficiency, there's an optimal window size for each particular scenario. And I think in this scenario, the optimal window size is 6 frames. You can check those numbers. I have a simple calculator that calculates that efficiency for you on a web page. It's linked from our course. It's quite simple. You just fill in some of the numbers. In this case, I've filled in some numbers already. Window size of 1 frame. 1. Set the data rate. Set the distance. And I can remember the values that I want. Sorry. One of the slides in your lecture notes gives this example. Data rate of 100 kilobits per second, propagation of 200 milliseconds, payload and so on. This example is the coloured one you have in front of you. Okay? If you do the calculations with this one, you get the same as the coloured printout. You'll get these numbers eventually. If I use those values, 100 kilobits per second, which is 0.1 megabits per second, I think we need a distance of 40,000 kilometres, e.g. some satellite. Same in both directions to get this this example that we've got. There's no processing delay in this question. And 1,000 bits of header is equivalent to 125 bytes. And 9,000 bits is 1,125 bytes. I checked before. No trailer. And the ACK. So it just allows you to set some of the parameters. Here it says the data frame has a header of 125 bytes, payload of 1,125 bytes. The ACK is simply 125 bytes of header. Time units, that's the time units of our answer. Let's give the answers in milliseconds. And the plot will come back to, and we calculate. And it calculates hopefully the same one as before. If we go down the bottom, we'll see the answer. The 510 milliseconds. I've left in the one microsecond of delay is still in there. That's the problem of this 0.001. But we get our 100 of transmission, 200 of propagation, 10 of ACK, total of 510, and with a window size of 1, efficiency of 17.6%. And you can change those values and see if you have a window of 3. And you can also plot that. So let's say I want to try for different values of the window size, the maximum window size. I want to try for values 1, the current value, up to 10. Then it calculates the same values, and at the bottom shows a plot of those values. That is window size of 1, 2, 3, 4, up to 10. At 1, the efficiency is 17%. At 3, we're about our 53%. And at 6, 7, 8, 9, 10, we're up to our 90% efficiency. So you can see how increasing the window size increases the efficiency up to some maximum there. And then if you keep increasing the window size, it will stay fixed at 90%. You can use that to see the impact of other parameters on the efficiency. By seeing a plot, you could see if you increase the data size, how does it impact on efficiency, and so on. So an example of how you can calculate that quickly. Of course, in the exam, you don't have that. You can do it on a piece of paper. One last example, which is shown here. What we've done so far is looked at a case where the source always has data to send, okay, which is the case where we can achieve the maximum efficiency. But of course, in practice, sometimes the source doesn't have some data to send, so the window size varies. And that's what this example tries to show. It shows the window at the source, A, and at the destination, B. And it shows some frames being transmitted. So initially, in this example, the maximum window size is 7. That's the blue rectangle. It goes from frame 0 up to 6. 7 frames are allowed to be sent. In this example, it sends 3. Okay? It's only got 3 data frames to send. It's got no more data to send, so it transmits 3. It's allowed to send 7, it transmits 3, so after transmitting those 3, from source A's perspective, frames 3, 4, 5 and 6 are allowed to be sent. 7 were allowed, it sent 3, 4 are now allowed to be sent. So that's the window, the current window size. From the destination's perspective, it keeps track of the frames it's expecting to receive. That's what the blue rectangle is. It's expecting to receive 7 frames and store them in the buffer. It's got space in the buffer to receive 7 frames. So if each frame was 1,000 bytes, then let's say it's got a 7,000 byte buffer. If it received 8,000 bytes, the buffer would overflow and we've got our problem. That's what flow control tries to avoid. So we've got space at the destination to receive 7 frames. We receive 3. So now we've got space for another 4, the blue rectangle here. In this case, we send back what's called here receive ready, which is just our acknowledgement, our ACK. It's saying, I'm ready to receive more. It's an acknowledgement of the frames received. And when we send an ACK, we include an acknowledgement number, and that acknowledgement number indicates the next sequence number I expect to receive. B has received 0, 1 and 2. The next one I expect to receive is 3. That's how our acknowledgement numbers work. They don't say the last one received, they typically say the next one expected to be received. So B sends back saying, I've received 0, 1 and 2. I now expect to receive frame 3. That is 0, 1 and 2 have been processed and effectively acknowledged. So what happened? B received 3 frames. It's got space in the buffer for 4 more, but then it processes those 3 frames and removes them from the buffer. And when it removes them from the buffer, it sends the ACK, and it's got space for another 3 frames in the buffer. A buffer for 7 frames, receives 3, it's got space for 4, but then it processes those first 3, and now it's got space for the full 7 again here. So sending an ACK is done when we're ready to receive more frames in our buffer. So in this example, we are now ready to receive the next 7 frames. When A receives that ACK or that receive ready message, it acknowledges the 3 that it's been sent. How do we know that? A has 0, 1 and 2 outstanding. The next one expected to be sent is 3. When we receive a receive ready saying I'm ready to receive 3, it means 0, 1 and 2 must be successful. So at this point in time, 0, 1 and 2 are transmitted and ACKed, meaning we're allowed to send 7 frames. We've got none outstanding in this case. So our window size covers the 7 frames here, the maximum window size. In this example, we now send 4 frames because, for example, we only have enough data to fit into to make 4 frames. We have no more data. 4 frames, 3 are allowed to be sent after sending those 4. 3, 4, 5 and 6 are outstanding. 7, 0 and 1 are allowed to be sent. From the perspective of B, and it's a bit different or a finer detail here, after receiving frame 3, B immediately processes that frame and sends back an ACK for that frame in this example. That is, it receives frame 3, processes it quickly, sends back an ACK or the receive ready saying I've received 3, receive is ready for frame 4. And from B's perspective, it's now expecting to receive 4, 5, 6, 7, 0, 1, 2. 7 frames. Then after that, it receives 4, 5 and 6. So 4, 5 and 6 have been received. They are stored in the buffer. 7 through to 2 are expected to be received. We have space in the buffer for another 4. Why did it happen like this? Well, it depends upon what's happening at the transmitter and receiver. That is, why do we transmit 3 and then 4? It depends on how much data they have to send. So it's up to what's happening from the higher layers and how fast they process the data. So it's just one specific case. It could have been different. B is expecting or is buffer to receive 4 more frames because it has these 3 in the buffer. A has 4 outstanding, 3, 4, 5 and 6, allowed to send another 3. Eventually receives this receive ready, meaning frame number 4 is the next one that's outstanding. 3 has been ACKed because B is saying I'm ready to receive 4. That implies frame 3 has been acknowledged because we do it in order. If 3, 4, 5 and 6 were outstanding and we receive ready 4, it means 4, 5 and 6 are still outstanding because B is waiting for frame 4. 4, 5 and 6, these 3 are outstanding, we're allowed to send another 4. And we could keep going, it doesn't continue any further. So this is just an example that we don't always send all 7 frames. We only send as many as we have available to send. It depends upon the data we have available. And again, you see the blue rectangle, this window, going from its maximum, 7, the maximum window size, and moving along, sliding across, moving in this direction. And as we transmit frames, closing on the left, getting smaller. As we receive ACKs, opening on the right, getting bigger. And that's our sliding window, a window that opens and closes and slides along. It's just a way to conceptualize what happens there. So this is much more complex than stop and wait, and that's the disadvantage of sliding window. In terms of implementing, it's more complex at the transmitter and receiver, and you need a buffer. With a window size of 1, that is stop and wait, with a window size of 1, the receiver needs a buffer, enough memory to store 1 frame. With a window size of 3, needs a buffer to store 3 frames. That's the idea. The window size, the maximum window size indicates the maximum buffer size at the receiver. The larger the window, the more efficient we can be, but we need a larger buffer at the receiver. Okay, that we use up more memory at the receiver. So there's one of the trade-offs that we need to consider. So sliding window, in summary, is generally more efficient than stop and wait, or it can be in certain links. It depends upon the window size. The main factors in the link that impact on performance are the transmission delay and the propagation delay, the relationship between them. Sliding window can be more efficient than stop and wait, but it's more complex and requires more memory at the receiver to work correctly. So it depends upon what your requirements are for the transmitter and receiver. That covers all we want to do for the flow control. Any questions on them before we move on?
This one is when you move like the next 3 bits. It's 3 is loading.
What this diagram is showing, both the sender keeps track of the frames it's sent and allowed to send. The receiver keeps track of the frames that it has received and expects to receive, which is the window, the blue part, or the rectangle is the frames from the sender's perspective that it's allowed to send at some point in time. and from B it expects to receive, or it can fit in its buffer. So they are different, okay, because it takes time to deliver the packets across the link. The perspective of A and B, and we see here the windows may be different at different points in time. Now, coming back to your specific question, does that help?
Why this one when you send the next or send the next 3 bits to here, this 3 is out of there?
No. So at this point, A is allowed to send 7 frames. Initially allowed to send 7, 3 were sent, 3 are acknowledged, it's allowed to send another 7. It sends 4. So after sending the first one, it's allowed to send another 6, then another 5, another 4, and then after sending the 4 frames, it's allowed to send another 3. What this diagram is showing is after receiving frame 3, B immediately sends back an ACK. It quickly processes that frame. That is, it goes into the buffer, then comes out of the buffer, making space for another frame. So after receiving frame 3, we were expecting to receive 7, we receive 1, expect to receive another 6, but process that and means we can now receive another 7 frames. This diagram doesn't show the window at every point in time, only in selected points in time. So it doesn't show at this point in time, here, 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 and so on. It only shows at some example points in time. I don't know if that's answered your question, but we'll see. Yep.
So this is what we can send, right? The 7.
Yes, the left side, the blue box here, is the frames we're allowed to send.
But if you send 4 frame here, it should be like 3, 4, 5, and 6 sending down.
It is here.
What
No.
on the right side, on the B side?
The left side is what A is allowed to send. The right side is what B has received and is allowed to receive in its buffer. They may be different because at some point in time A has sent some frames, B hasn't received them yet. They're flowing across the network, across the link, because it doesn't happen immediately that we transmit and receive. There's a propagation delay. So A has transmitted and eventually B receives.
Why did it start from 4?
Why does this one start from 4? Because we start at 0, receive frames 0, 1 and 2, 0, 1 and 2. We now expect to receive 3 next. And then we receive frame 3. So if we drew the box here, we receive frame 3, but now immediately we send the ACK for frame 3. So this is after receiving and then sending the ACK. So let's draw it in a bit more detail. Frame 3. Before, that's here, we have this is at this point in time at the receiver. Receive frame 3. It becomes when we receive frame 3, we've got space for another 6. Frame 3 has been received but not yet ACKed. And now we send the ACK, which is the RR4 here. And it becomes 3 has been received here, and now we've sent the ACK for 3, so it now becomes ACK. And we're allowed to send another one. And that's what we get here. Okay? So be careful. This doesn't show the window at all points in time. At this point, you can see it's received and then ACKed. So the diagram shows this one and this one. It doesn't show the intermediate one. Okay? Just because of space. So that's at the receiver in that specific case here. This receive, transmit the ACK, or the receive ready. Any other questions?
Does the window size be always be 7 with 3-bit sequence? But you say that abnormal window size 6.
Okay, so the question is about the window size, and we had here, or in the coloured example that you had, we had a 3-bit window, a 3-bit sequence number. Here we had a 2-bit sequence number. With a 2-bit sequence number, we can represent the values from 0 to 3. The maximum window size we can have is 3 in that case. And similar with a 3-bit number, the maximum value we can have is 7. We could have a lower value than 7. We could have, with a 3-bit sequence number, a window of 6, W equal to 6. We can do that. There's nothing to stop from that. But it's common to make use of all the bits. If I've got 3 bits, I can go from 0 up to 7, so a window size of 7 is possible. But a window of 6 is also possible. So yes, you can have, although I use 1, 3, 7, it could be 1, 2, 3, 4, 5, 6, 7. That's okay.
Can I have more? For example, 4, because I will spend less time.
Okay, then the question is, can you have more? And the answer is no. With a sliding window, with a k-bit sequence number, the maximum window size is 2 to the power of k, all minus 1, with sliding window. We don't have time to explain that, and it's a difficult one to explain, not just for this and also the next topic. Well, there's another variation. The textbook has a very good example that illustrates if you had larger, what would go wrong. If you had a 3-bit sequence number and you had a window of 8, something could go wrong. It will not work. The protocol will not work. Okay? So there's a limit. With a k-bit sequence number, the maximum window with sliding window is 2 to the power of k minus 1. Check the textbook for an example showing why that's the case. We will not go through that in this course. Before we look at error control, any last questions? Note that error control is based on these mechanisms. If you don't understand these, you won't understand error control. Any questions? We're not onto these lecture notes yet. You're too far ahead. Yep.
So after the RR4, we got an error because there is no frame 4.
After the RR4, which is really an acknowledgement saying I now expect to receive 4. So what, from A's perspective, it has sent 3, 4, 5 and 6. Then it receives an ACK, and this is a bit strange. It receives an ACK saying I'm expecting to receive frame 4. From A's perspective, it knows, okay, I've sent 3, 4, 5 and 6. B is expecting to receive frame 4, that implies frame 3 was successful. Okay, so that means frame 3 is now complete. It's not an error, nothing's gone wrong. We do not have to retransmit 4, 5 or 6 because we know that there's some delay in which it takes the frames to get to the destination B. So yes, we receive the ACK for frame 3, but we expect or we hope that sometime later we'll eventually receive the ACKs for 4, 5 and 6. And if we have no errors, we will. So nothing's gone wrong here. It just says that frame 3 has been ACKed. 4, 5 and 6 we'd say are still outstanding. I've sent 4, 5 and 6. I'm still waiting for the ACK. They haven't yet been ACKed. Eventually we should receive them as we go on down below.
The first acknowledgement, the B send R3 back. Then one is for R1 and R2.
Yeah, this first acknowledgement or receive ready is what we sometimes call a cumulative acknowledgement. It acknowledges 3 frames at once. It says we receive 0, 1 and 2. By sending the number 3, it means thank you, 0, 1 and 2 have been successful. I now expect 3. So rather than sending 1 ACK, 2 ACKs, 3 ACKs, we can be more efficient and simply send 1 ACK saying acknowledge all 3 frames at once. That's the idea there. So there's different ways to do it, but that illustrates 1 ACK acknowledges 3 frames as opposed to 1 per frame.
How will you know if we will send R3 or R1, R2?
So the next question, and it's a good one again, is do this or send RR1, RR2, RR3. That is, send 1 ACK for 3 or send 1 ACK for each frame. It depends upon the specific protocol and it depends upon the implementation. In practice, it varies. Okay? There are different factors that determine when to send the ACK. In general, you can do either. In a question in the exam, I'll tell you which one. Okay? But in real life, it varies amongst different protocols. So now you are experts in sliding window. Let's see, and also stop and wait. Some extra features. Some things that we haven't shown, but you can extend to add different features. You can have we saw a receive ready frame, which I really call an acknowledgement. We can have a receive not ready frame. To acknowledge frames, but say we cannot send any more data. So that's another case. We can piggyback data and ACKs. What that means is that we can send 1 frame which contains data and also an acknowledgement. Let's illustrate that. In all the examples we've shown, we've seen data going in one direction only, from A to B. In real life, often A wants to send data to B, and B also wants to send data back to A. We'd like to send data in both directions. That's common. If we do, then we can be a little bit more efficient in using this concept of piggybacking. And it's not just for sliding window, it also applies for any protocol. How do we draw it? I'll do it for stop and wait. Here's an example with no piggybacking. A wants to send some data to B. It sends some data, B receives the data, sends back an ACK. That's normal stop and wait. And also B wants to send data to A. So after sending the ACK, B sends some data to A, and then we may get an ACK back here, and so on. Piggybacking is simply combining these into one frame. We think this is the data A plus ACK 1. A sends data to B. B needs to send back an ACK, but B also wants to send data to A. So B creates one frame which contains both pieces of information, both the data and the ACK. And that's the concept of piggybacking. It saves in transmission time. Send one frame, and instead of sending an ACK and then another data frame. So it's just a way to make our transmissions more efficient. If I was to draw a data frame, there's a header and some data. Inside the header, we normally have at least a sequence number. An ACK frame is normally just a header and contains an ACK number. Sequence number and ACK number. For example, this data frame has sequence number 0, this ACK name has ACK number 3. This piggybacked frame has a header, data, and in the header there's both a sequence number and an ACK number. So basically we combine this into one frame, that's all. So this, let's call it a data plus ACK frame. We're sending an acknowledgement for the data we just received, and at the same time sending some data in the opposite direction. That's all. That's this case. And because it effectively reduces the size of the header, if we use two separate frames, we send the header twice. If we use one combined frame, we've cut down on the overhead. That's the idea of piggybacking, just cut down on the transmission time. That's possible, and it's commonly used in many protocols. And there are some other extensions of sliding window that can improve the performance or slightly give lower overheads. We'll see piggybacking come up when we look at some more specific protocols later. But combine the two frames together as one frame. So flow control, remember, is about control the speed at which the sender sends such that it doesn't overflow the receiver. Error control is about fixing errors. If I send some frames and there are some errors, by errors maybe a frame doesn't arrive, somehow it gets lost, then if that data is not correctly delivered, get the sender to send it again. That's the error control mechanisms we'll look at. Retransmit that data and what protocols we can use to provide error control. Why do we need error control? And we mentioned before about the topic we skipped over on error detection, error correction. In real life, links may have errors. We send some bits. The bits received at the receiver do not match what were actually transmitted. If that happens, we need to fix it somehow. And this is what we're going to go through, how we use error control protocols to fix the delivery of the data. And the approach that we're focusing on is very common. we simply ask the sender to send again, to retransmit. When we're talking about frames, we can distinguish between lost frames and damaged frames. A lost frame is if I transmit a frame from A to B and it doesn't get to B. Okay? The entire frame doesn't arrive at B. Maybe the link fails for some period of time. Maybe I transmit a frame out of my computer, the link goes down. Of course, B will not receive the frame. We say that entire frame is lost. Another case is I transmit a frame from A to B. A transmits the frame. Some of the bits in that frame arrive in error. So we transmit a frame with 1,000 bits. Some of those bits are wrong, and that B can detect that. We'd call that a damaged frame. A frame is received with errors. We'll normally treat them the same. That is, if we lose a frame, the receiver didn't receive it. If the receiver receives a damaged frame, the receiver would normally throw it away, discard that frame, as if it's never been received. The topic we skipped over was on error detection and forward error control. We're looking at different techniques for error correction. 3 main approaches: positive ACKs, retransmissions with timeouts, and negative ACKs. A positive ACK is I send a frame. If the receiver receives it correctly, they send back a positive acknowledgement saying, thank you, I received that frame correctly. Okay, that's if everything goes fine. In that case, if I send a frame, I expect to receive a positive ACK back. I send a frame. If it's received successfully, I should receive an acknowledgement back saying, thank you, I received that. If I send a frame and I do not receive an ACK back, I may retransmit. Okay? And we have some timer value to work out how long to wait for the ACK to come back. I send a frame. I expect to receive an acknowledgement back. If after some time I don't receive an acknowledgement back, then I'll assume it's been lost and then I'll retransmit. So this is the concept of retransmission after timeout. Send a frame, wait for an ACK. If there's no ACK after some time, send it that frame again. And hopefully it's received and we'll receive the ACK back. If not, send again. And send again. In practice, there'll usually be a maximum number of retransmissions, after which I'll give up and report there's some error. The other approach, and I don't think we'll see many examples, is a negative acknowledgement. I send a frame. The receiver recognises that there's been some error and sends back an acknowledgement saying, there's been an error. Please send this frame again. Okay, so this is a negative acknowledgement. It's an acknowledgement saying there is an error. Please send again. A positive ACK is an acknowledgement saying that there was no error. Keep sending the next piece of data. Okay, we'll see. Actually, we will see some examples of that. Acknowledgements, retransmissions, timeouts, these mechanisms together are referred to as automatic repeat request mechanisms, or in short, ARQ. So these, we're going to go through 3 variations of ARQ protocols. Protocols that use these mechanisms, and they are based upon the flow control mechanisms. There's a stop and wait ARQ, which is the simple one. And then there's 2 which are based upon sliding window, where we can send multiple frames. One's called go back N, and one's called selective reject. But remember, these are not for flow control, although they use the same or similar mechanism. The purpose of these ARQ protocols is to perform error control. If we lose data, retransmit. And these are the schemes of how to retransmit or when. We'll go through stop and wait ARQ first. And as the name suggests, it's based upon stop and wait flow control. Send a data frame, receive an ACK. send a data frame, receive an ACK. But what the source does now is it sends a single data frame, and after sending, it starts a timer. Okay, so it starts a timer, and it waits for an acknowledgement to come back. If an ACK is received, then it stops the timer and moves on to the next frame. So if everything's okay, send a data frame, receive an ACK, send the next data frame. But if we send the first data frame, we start our timer, and no ACK is received before our timer expires, that it reaches some value, then we retransmit a copy of the frame. So if we don't receive an ACK within some timeout period, retransmit. We'll see some other mechanisms, but let's illustrate that. Here we have A sending data to B. At the start, A has some data to send, sends the first frame, transmits it to B. B receives, processes the data, sends back the ACK. Everything's fine. The ACK arrives back at A. A had data to send at the start, it sent it. Again, it's stop and wait. We cannot send two frames. We transmit one frame, we're waiting for the ACK. Even though we have more data to send, we must wait for the ACK. Okay? Same as our stop and wait flow control. We cannot send the next one before we receive the previous ACK. We receive the ACK, everything's fine, and then we transmit the next frame, which is the data here. Arrives, data is processed. We say the data is delivered to the higher layer at the computer B. That is, data is received, processed, and then delivered to the higher layer, and then send the ACK back. So the data has been successfully delivered to the destination. Here we receive the data frame, process, it takes some time. Data is delivered, everything's okay. Data 2 that was sent, send an ACK. Data 3 is sent, and we'd see an ACK coming back. This is the normal case. No data is lost. That's easy. It's simply stop and wait. We introduced sequence numbers. In stop and wait flow control, we didn't need sequence numbers. In stop and wait ARQ, we have sequence numbers. 1-bit sequence numbers. With a 1-bit sequence number, the values are 0 and 1. 0, 1, 0, 1. So we see that in this diagram. Sequence number 0, ACK. Remember, the ACK indicates the next sequence number expected. B has received data with sequence number 0. Thank you, I now expect data with sequence number 1. That's how we interpret the ACK1. A transmits data with sequence number 1. B, after receiving and processing that, says, thank you, I now expect data with sequence number 0. We have a 1-bit sequence number. We just alternate 0, 1, 0, 1, 0, 1. And so 0, 1, 0, 1 if we keep going. So this is what we've seen with stop and wait flow control. What happens when we lose data? Let's try and draw it. Let's get some colour. So that was the case where all our data was delivered successfully. What happens if something goes wrong? This is our data, and sequence number 0 in this case, so we start at 0. So to follow the previous case, we had some data, I'll call it data 1. A has some data to send to B. This is the first piece of data. Transmit, everything's okay, it arrives. Deliver that data. So we say data 1 delivered successfully. We've received it. Okay. So we send back an ACK. with sequence number or ACK number 1, because the next sequence number we expect is 1. So if we follow the previous slide, we had data 2, transmit data 2, which is actually sequence number 1. We transmit data 2, it doesn't get to the destination in this case. There's some error in the link. We transmit the frame, B does not receive it. We say this is a lost frame, a lost data frame. What happens? Well, after transmitting the data frame, although it's not shown, the source starts its timer. Okay, it starts a counter. So I'll draw that here. Start timer, and there's some maximum value of the timer. If the timer reaches this maximum value, we say it's a timeout has occurred, and that will trigger a retransmission. So A transmits the data. It's lost somewhere. B is never going to receive it. Therefore, B is never going to send back an ACK. B is just going to wait for more data. It's not going to receive data, so there'll be no ACK coming back. So what? A is waiting for the ACK, it's waiting, and then at some point in time, the timer reaches some maximum value, and that's a parameter as part of the protocol. We say a timeout occurs. Let's say we wait for 1 second. Transmit. Wait for 1 second. If we don't receive the ACK within 1 second, a timeout occurs, and in that case it triggers a retransmission of the data. Data with sequence number 1. This was data 1. This contained data 2. This is exactly the same as the previous one. The second piece of data. And let's keep going. So the first thing we see now, if we don't receive an ACK back within some time value, retransmit. Retransmit means send the same data frame as previously. And that data frame, propagates and eventually arrives at B. So in this case, there's no error. Everything goes fine. B receives the data frame, processes, data 2, okay, sends an ACK. And the ACK number is, the ACK number is 0. B has received data with sequence number 1. So if you follow my diagram, data with sequence number 1 is transmitted here. It's propagating across the link. It's propagating. Data with sequence number 1 is received here. And then we send an ACK with sequence number 0 back. We just alternate 0, 1, 0, 1, 0, 1. And then we can send the next piece of data. No need to draw that. Data sequence number 0, which is the third piece of data. The black numbers in here indicate the pieces of data that we're sending. The first, the second, and the third. Wait for an ACK. If you don't receive an ACK within some period of time, retransmit. Any questions on that one? So that's illustrating one part of the stop and wait ARQ. Yep.
What is the number at the back?
The number in the brackets is the sequence number of the data frame, or the ACK number of the acknowledgement frame. So this is when we send a frame, a data frame, we have a sequence number. When we send an ACK frame, we have an acknowledgement number. And I've drawn that in brackets. Sequence number 0, 1, 1. Because it's a retransmission, we use the same sequence number. It's only on new data do we send a different sequence number. If we keep drawing, it'll be 0, 1, 0, 1, 0, 1. And the ACK is the next sequence number expected. Receive 0, expect 1. Receive 1, expect 0, and so on. Any other questions on that case? Because your next task is to complete the next case.
What will happen if got error?
So your task, draw if we lose an ACK. So draw the diagram, assume the first data and ACK successful. The second data is successful, but the ACK is lost. What happens? Draw that. So I'll start it, you'll finish. First one, okay. Same as before. Second one, data is okay. Delivered. Send an ACK. Lost. What happens? Continue that diagram. So try and complete that diagram. This is the case of a lost acknowledgement. If you cannot see the red, then this is simply we start the timer. In fact, we start a timer here, but we receive the ACK before the timeout. Here we start the timer. We don't receive an ACK, so we time out. Triggers the retransmission. Try it when you lose an ACK instead. And think about what is delivered or what is not delivered to the destination. This is indicating we receive the frame, we deliver that data to the higher layer. We deliver data 1. Data 1 is created, received. Data 2 is created at A, received at B, and so on. Consider also that when you lose an ACK. What data is delivered to the higher layer? So the first data ACK is the same as in the slide on the screen. What happens? The first data is successful in this case. Ignore that one. Second piece of data, A transmits. It arrives at B. B processes, delivers that data to the higher layer. Everything's fine. So therefore, B sends back an acknowledgement saying, thank you, I now expect more. The rules of our protocol are the source, A, sends a frame. After sending the frame, it starts a timer. So here, it starts its stopwatch. And it's counting, and if it has a maximum value. Okay, so it's starting at 0, 1, 2, 3. It has some maximum value, say 10. If there's no acknowledgement received before the timer expires, we retransmit. We've sent the data from A's perspective. We're waiting for the ACK. We're waiting. We're not going to receive the ACK because the ACK was lost. So we're going to keep waiting until our timer expires. I'll draw that simply here, and we often call it just a timeout. The timer expires, a timeout occurs. We've waited too long, or waited long enough. That triggers a retransmission. If we continue, our timeout occurred. When that occurs, then computer A assumes that the data that it sent, something's gone wrong. There's been an error. It doesn't know if the data's been lost or the ACK has been lost, but it knows something has gone wrong because it expects to receive the ACK. If it doesn't receive the ACK within a reasonable time, then it assumes something's gone wrong, and when it assumes something's gone wrong, it resends. Draw it a little bit bigger. The data sequence number 1. It's the same sequence number as this. It's the same data, the same frame. It's a retransmission of this frame. So sequence number 1. That arrives at B. What does B do? So in this case, we retransmitted because we didn't receive an ACK. What does B do? Sends ACK back. Correct. what else does it do with... Look what B did. B received data and sent the data 1 to the higher layer. Everything's okay. Remember, although it's not drawn, on the next slide, we show the first piece of data, the second, the third piece of data is delivered, successful, data 1, data 2, data 3. Same here. Data 1 is delivered successfully. Data 2, from B's perspective, was delivered successfully. It received data 2, sent an ACK. But now it's received data 2 again. Because this is the same. It's a retransmission. So we will say that I can discard or ignore the data. B has received data 1, okay. Received data 2, okay. Received data 2 again, throw it away. Ignore or discard that data. Because we don't want to receive a duplicate of that same data. So in this case it discards the data, and the reason it knows to discard is because the sequence number is the same. Before it received data with sequence number 1. And now, immediately after, it's received data with sequence number 1. That tells B that this is the same as the previous data. Because B should receive data with sequence number 0, 1, 0, 1, 0, 1. If it receives data with sequence number 0, 1, 1, ignore that data. But still send an ACK. That is, ignore the data, but send an ACK saying, I'm expecting, what's the ACK number? I'm still expecting 0. And the same here, ACK 0. I've received 1, okay, I'm expecting the next, which is 0. And then when we receive the ACK, we can move on to the next one, data 3. So what happened? Computer A, the same rule. If you don't receive the ACK within some time period, retransmit. So that's the same as whether we have lost data or lost ACK. So there were two different cases. Lost data, send the data, it was lost, we don't receive an ACK, retransmit. Lost ACK, we don't receive the ACK, retransmit. And also at B, if you receive data frames with the same sequence number as before and you've already acted, ignore that data. Receive data sequence number 1, okay. Receive data with sequence number 1 again, discard or ignore that data. We don't want to receive the same data and process it twice. What if the data was reduce the student's grade by 10 marks? So data 2 contained the message, reduce your grade by 10 marks. Okay? And then, so data 2 has reduced your grade by 10 marks. B receives it, reduces your grade. If we receive that same message again because it was retransmitted, you don't want to reduce your grade again, okay? You want to just process that data once. It's just one piece of data. Even if it's retransmitted, ignore future copies. So that's what happens here. Here's the original data, received, okay. A copy, received, discard. If you receive another copy, discard. They are the two main cases with stop and wait ARQ. Any questions on that before we have a break? Let's have a break for 20 minutes. Come and ask me questions. After the break, we will cover go back in and selective reject. Okay?